Okay, part 2 of most commonly missed problems. Again, I suggest pausing the video, reading the question thoroughly, and then unpausing to get my comments. On this question, I think the biggest issue is realizing that it's really just a one sample t-test. So if we make sure we get the direction correct, so newly designed minus before the old design, so that means we're taking 77 minus 84, that would give us -7. And then here we would have 88 minus 87, which would be 1. So you're just going to go through. You could do it manually. You could put all these scores into SPSS and run it as in the lab assignment, but it's just as easy to go one by one, get these 8 scores, and then handle them exactly like you would a one sample t-test. The null hypothesis is going to be that difference score equals 0. When we say difference score, we mean this set of new data points we're collecting here, which makes sense. On average, the new design score minus the old design score should be 0 if the null hypothesis is true, if these clubs really don't improve or deprove the scores at all. And then the alternative, so here we need to look at the question. This is fairly important. The manufacturer's claim was that the golfers can lower their scores. So they're saying that the new design would be lower than the old design. So when we take these new design scores minus the old design scores, that's what our difference scores, that's what's creating our D sub I, our difference scores. On average, they should be less than 0. They should be negative. These numbers should be lower than these numbers in general if that manufacturer's claim is true. The standard deviation, this would be the same as sample standard deviation. So once you have these 8 data points, the difference scores that you get from subtracting the lower number from the upper, and the only reason I'm saying lower minus the upper is because of the direction that was determined here. That could be different in a different problem. But then I would just use the calculator or SPSS to get the sample standard deviation for those differences. The test statistic, same thing. We could do a one sample t-test in order to get that t-test statistic. P-value would be a one sample t-test and looking for the p-value there. Do notice that it's a one-tailed test. It's a left-tailed test like we set up in step 1 with an alpha of 0.1. And we would either reject if there was sufficient evidence, in other words, if the p-value was below 0.10, or we would fail to reject if our p-value was above 0.10. Okay, any question like this, I really think the best thing to do is create a visual. So we have a normal distribution here, and let's say this is our mean, and we have 97.22. So we have this huge area right here is 97.22%. What we need to do is get this value of z, or -z. And there's a couple ways we could do that. One way is we could split this number in half, so just divide this by 2. That would be the portion just in this area right here. And once we have that, we could use the normal table 0 to z, find whatever that number was, so 0.48 something. We would find that, and that would give us our z-score. Alternatively, the other thing we could do is to, is to take whatever's in the tail, so take 1 minus this, get 0.2278, and then split that in 2. That would give us the portion that was in this tail right here, And in that case, we could get negative infinity to negative z. We could find that portion, and that z-score there would give us the answer. So either way, if you draw it out, it's easier to figure out how to look it up on the table. This would be a similar type of deal. In this case, we have 0.08 right here. So I'd say the easiest would be to look up on the z table. So negative infinity to positive z. We're past the mean right here. We're well past the mean. So negative infinity to positive z. Look up 0.92 because that standard normal table always gives you whatever to the left. And if you look up 0.92, that'll give you the z-score that's right here. The other thing you should notice is when we are looking it up on this table, we are not looking here. We don't have the z-score yet. That's what we're trying to find. What we have is the portion to the left, so that's why we need to look in the body of the table. And we would get as close to 0.92 as we could, either one of these, and then take 1.40 or 1.41 would be our answer in this case. Okay, these questions trying to figure out what kind of data we need. Anytime we only have two possible outcomes, that's going to be qualitative. As soon as we select qualitative, whether it's nominal or ordinal, either one of those would be considered qualitative. Nominal would be a category or a two possible value response, something like this. Or ordinal would be a ranking, like in a race, first, second, third, fourth, fifth. Either one of those would be qualitative. As soon as we hit that, we're going to say that it's neither discrete nor continuous. Qualitative is going to be neither of those. And here's where we choose. So qualitative is these two are quantitative. In this particular case, we just have two possible outcomes, two categories, so this would be nominal. Okay, so here we have an average time that the drug stays in the system, and we have a sample and the sample mean here. This is the key statement. I think this is where most people will get tripped up. So the population variance is known to be 289. So first of all, we probably want to take that to a standard deviation, and that we could do that by taking the square root of this number. The other thing is to try to figure out if we're doing a Z procedure or a T procedure. Since in some weird way here we actually have the population variance or the population standard deviation, we know sigma. In other words, sigma is known, which means since it's either normal or it's above a reasonable sample size, above 30, for example, we can go ahead and use a z-test procedure. So we don't have to use a t procedure for this problem. We can go ahead and use a z procedure on your calculator. Would probably be the easiest way to do this. One sample z-test.